I'm Robert Edmonds. This is Paul Vixie. If you came to see him, you might be disappointed because he's got a little 10-minute thing at the end. The talk we're covering today involves passive DNS. Hopefully, most of the attendees here are familiar with the DNS in general. Can I see a show of hands, people who know what the DNS is? Okay, very good. How many have read one or more DNS RFCs? Excellent. How many of you have heard of passive DNS? Okay. I'll probably skip over the introductory material as fast as possible because I have way too much material. I'd like to get to the demos, but in order to understand why the demos are so cool, you do need a certain amount of depth. So let's get started. This is the structure of the talk. There's 4 parts. I'll skip that. Okay, so the DNS maps host names to IP addresses. This is generally what we consider it to be, but in fact, it's more of a more generalized system. It's basically a distributed key value system. More generally, it maps key type tuples to a set of unordered values. Yeah, so basically a multi-value distributed key value store. Excellent. Some terminology. We have clients, caches, and content. There are 3 fairly well-defined roles in the DNS. Clients request full resolution service from caches. Caches make 0 more inquiries to content servers on behalf of clients, and the results are cached. And we have content name servers, which serve the DNS records that have been delegated to them. And here's a PowerPoint diagram showing the hourglass nature of this delineation. You can see that an ISP might have millions of clients, and these clients are everywhere, phones, laptops, whatnot. And there are millions of content name servers because there are millions of domain names that people want to look up. But you have very few DNS caches. Even the largest ISPs have around 100 100 DNS caches or less. So we have this natural choke point where we can insert a monitoring application. The DNS, so I just explained we have 2 different, so we have 2 different protocols. One that the cache speaks to the client speaks to the cache, and one that the cache speaks to the content name servers. And these are fairly different semantics, but they use the same wire protocol. So the DNS is commonly considered to be, port 53, but it's terrifically complicated. So the 2 protocols are the client server protocol and the inter server protocol, spoken between caches and content name servers. Passive DNS focuses on the latter because we don't want to see client queries or give the impression that we are spying on people. In fact, what we want to do is gather intelligence about the domain name system rather than clients that are requesting that information. So passive DNS replication was invented by Florian Weimer about 6 years ago, who found a variety of uses for the technique. And the most impressive use of that to date has been in combating malware and e-crime. So domain names are so cheap as to be basically free, but infrastructure and numbering resources are not. And the sharing of that infrastructure to host multiple e-crime campaigns makes it possible to track and link malicious uses of the DNS. And just to give one example, fast flux botnets light up the passive DNS like a Christmas tree. Passive DNS replication basically consists of a number of passive sensors that listen to the packets that are generated when a DNS cache performs a lookup. The packets are then forwarded to a central collection point for analysis. After the packets captured by a passive DNS sensor are submitted to the collection point, they're then parsed and analyzed and reduced into a stream of individual records that we then permanently store in a database. And here's a picture of our DNS architecture again, where caches talk to content servers. We've taken the clients out of the picture since they're not particularly relevant to passive DNS, and we've inserted a sensor between the caches and content showing how passive DNS monitors and forwards the inter-server traffic to a collection point. And that collection point is called SIE, or Security Information Exchange. We'll cover that as briefly as we can because the main thrust of this talk concerns the database that we build based on that data. So there have been a number of different implementations of passive DNS over the years. The original is Florian Weimer's DNS logger, whose backend was initially hosted at RusCert and then at BFK. Florian's implementation uses a custom libpcap forwarder on the passive DNS sensor and a Berkeley DB database for permanently storing that data. Then we have Boyan's DNS parse out of New Zealand, which uses a fairly primitive TCP dump-based sensor and a MySQL database. And the most recent and, to our knowledge, largest implementation is in ISC's Security Information Exchange, which inserts an elaborate distribution layer between the passive DNS sensor network and the analyzers of the captured data. And we use a custom analyzer that is hardened and more advanced than the analyzers used in DNS logger or DNS parse. And our storage components have been similarly hardened and have advanced functionality for dealing with the large amount of data that we collect. There may be other implementations, but I don't know of any other publicly known passive DNS implementations. This brings us to ISC SIE, which we'll describe briefly, and only the features that are relevant to passive DNS. So SIE is a distribution network, as I said, for replicating the security data from multiple sources to private secure LANs, where the data is broadcast to trusted consumers, including ISC itself, of course. One of those types of data is, of course, passive DNS. Passive DNS sensor operators run sensor code that captures DNS traffic and periodically uploads it in batches to our submission servers. And our submission servers take care of replicating the data among physical SIE sites where the data is broadcast out in a standardized format on private VLANs, sort of a poor man's multicast. And we use a standardized interchange format called InMessage, which we use to encapsulate the data. It's an extensible binary format that we've optimized for real-time transmission on jumbo frame Ethernet. And we use this format to record the raw packets that are captured by our passive DNS sensors. And this allows us to add a good deal of metadata along with the raw messages. So for instance, instead of storing a flat stream of packets like your typical PCAP file, we embed both the query and its response, and its corresponding response into a single message, which we can then process as a unit, rather than groveling through an entire PCAP file. And we don't really need to cover data message anymore, but you can see our Google Tech Talk, where we describe just that format at that URL. And this is the end of our introductory material, and we'll move on to some ancient DNS security issues and the analogs that they present in passive DNS. Unfortunately, nothing short of universal DNSSEC deployment really helps us, since passive DNS operates on a lower level than DNSSEC. So we have to be able to handle signed and unsigned data in as secure as fashion as possible. So we won't be discussing DNSSEC further. So what DNS security issues are most important to passive DNS? We have cache puraf poisoning, which is an old, easily defeated type of DNS cache poisoning from the 90s. And we also have Kamensky poisoning, which is a particular type of DNS cache poisoning that makes use of spoofed response packets. Actually, spoofed responses in general are very harmful to passive DNS data collection. Let's see. Cache puraf poisoning is the name of a type of DNS cache poisoning that occurs when a content name server appends extra records to a response. It's particularly insidious because an attacker can poison any record in the entire DNS tree simply by running a content name server and tricking clients into looking up a DNS name under the control of the attacker. So that's very easy to do. Here's how the attack works. The attacker runs a content name server, and a client is enticed to look up a domain name under the attacker's control. And the cache contacts the attacker's name server, and the attacker's name server provides extra records to the cache. And these extra records are inserted into the cache instead of being discarded. I'm going to skip the actual example because it takes a while to explain, but the idea is that we have a malicious.example.com name, and we trick someone to look it up, and suddenly this unrelated name, www.example.net, points anywhere we want. So the blue one and the red one is malicious, the blue one is suspicious but not illegitimate. Actually, let me go back. The gray record there is the malicious one, and it gets scrubbed out by DNS caches. modern DNS caches. I think we can sort of skip this slide. We can also skip this one. And we can skip this one. Okay, now that we've covered all the background material, as we lead up to the meat of the talk, how is this particularly relevant to passive DNS? So, Florian Weimer in his 2005 paper identified several problems with validating the data collected by a passive DNS sensor, but he chose not to implement protections against these problems. But we would like to fix these problems if possible. So we have the two problems in passive DNS that are sort of analogous to the two problems in this active DNS. And the problem with cache pref poisoning in passive DNS is that we can't see the DNS cache's internal state, so they can't recover what's called the bailiwick that the cache associated with a particular response. Bailiwick is entirely in the eye of the beholder. And this leads to a problem we call record injection. And the problem with spoofed responses is that they're treated just like normal responses by the passive DNS sensor. And a single spoofed response can poison the passive DNS database. So this kind of worries us because it makes passive DNS databases sort of an unreliable tool if an attacker explicitly wants to target a passive DNS database. So anyway, we'd like to make sure that passive DNS is at least as reliable as active DNS as far as resilience to cache poisoning goes, for whatever that's worth, in order to avoid allowing passive DNS to itself become a target in addition to the DNS. So let's move on to the protections that we've implemented on top of the basic passive DNS idea. It's actually relatively easy to protect the capture stage from spoofing. In order to make our DNS sensor at least as reliable as the DNS cache that it's monitoring, we need to capture both the outgoing queries that the cache is generating and the incoming responses that it gets back. So current generations of passive DNS only capture the responses, and they don't have the context or the state that is generated by the actual query that went out. So what we need to do is capture the outgoing queries and correlate them with the responses and verify that they fit together and form a valid transaction. In most cases, we need to verify that 9 different fields between the query and response are identical. And those are the 9 different fields that we don't have time to discuss, but basically we match them together and we can tell exactly which ones are valid, exactly which transactions are valid and which ones appear to lack the additional state to verify that they're valid. So ISC has released a tool called DNSQR that performs DNS packet capture and validates the query response pairs that are seen on the wire. DNSQR temporarily keeps each outgoing query packet in memory in a state table, and when a response packet is received, we do a lookup against that state table. And then the state table is keyed on that 9 tuple that we just skipped over. We can skip this. It's interesting, but we don't have enough time. There's blah, blah, blah. There's IP reassembly, which I won't explain why that's cool. So now that we've eliminated this spoofing vulnerability in the capture stage, we can move on to the data that is valid, or the data that has been captured and has passed all these checks, but happens to be attempting to redirect us, the cache pref style poisoning. So caches internally associate a bailiwick with each outgoing query, and bailiwick is sort of equivalent to the zone, but not really. It's a good enough approximation for this talk. So cache pref poisoning is pretty much identical between active DNS and passive DNS, and the solution is we're going to keep track of which zone or bailiwick that we expect the answer to be contained in, and we're going to discard any response records that aren't contained in that zone. And of course, nothing in the wire protocol indicates the bailiwick that the cache is expecting. So When we're looking at a particular DNS query response pair, we don't see anything in the packets that help us determine the bailiwick either. So we have to determine it ourselves from first principles. That's a relatively minor point. So we have to develop an algorithm that operates entirely passively. It's not allowed to make any inquiries of its own. It has to passively process each message and tell us for each record name in the response whether the IP address that sent us this response is really allowed to assert knowledge for that name. And this algorithm must provide a true or false value. It can't be a heuristic. We can tolerate a small number of false negatives if we have incomplete knowledge, but we cannot tolerate any false positives. That is the passive DNS bailiwick algorithm analyzes a DNS response and answers the question, for each record name, is the response IP address a name server for the zone that contains or can contain this name? For example, the root name servers can assert knowledge about any domain name and pass the bailiwick verification algorithm. And the GTLD servers, the .com and the .net servers, operated by VeriSign, can insert knowledge about any domain name that ends in .com or .net, and in fact they did so for a short period in 2003. It's called VeriSign Site Finder. Very good. So here's how the algorithm works. First, we allocate a whole bunch of memory that will be used to cache the name server and address records after they've been verified by the algorithm. And we call this cache the bailiwick cache. And we initialize this cache using the entire root zone, which will give our algorithm knowledge of where the root and TLD name servers are, and thus it will know the bailiwicks of all the root and TLDs. Then, when we want to verify a given name against a given name server address, we find all the possible zones that the name could be located in, and whether the name server address in the response packet matches any of the addresses that are name servers for these possible zones. And finally, each time the algorithm successfully verifies an NS, A, or quad A record, that record is then inserted into the bailiwick cache. We're going to skip through the algorithm examples because they take a real long time to explain, and we want to get to the demos. Okay, what we call DNSDB is basically a database for permanently storing DNS records from a variety of sources along with a certain amount of metadata such as timestamps. Our primary data sources are passive DNS data, as well as a number of zone files that we have access to. Each record is serialized as an array of bytes, which we then store in an Apache Cassandra database. We don't have enough time to go over the exact serialization scheme, unfortunately, because it's really neat. We chose Apache Cassandra for a number of reasons. In particular, it's a distributed key value store, which means we can scale easily as the size of the database grows, and its data model provides a good fit for the type of data that we want to store. It's also extremely fast and can easily keep up with the amount of data that we need to process, primarily due to the fact that Cassandra always performs sequential writes, so we can make use of cheap, slow SATA storage. We then export the data stored in our DNS database via an HTTP API intended for bulk queries, as well as an interactive web search interface. And since we started loading data about a month ago, the size of our database has grown to about 500 gigs out of 27 terabytes total storage that we've deployed. We just bought some small little 2U boxes to test the thing out. DNSDB consists of several loosely coupled components. We have a number of data sources from which we receive new DNS data. And that's first most important source, of course, is the passive DNS. Oh, okay. The first and most important source of DNS data comes from a program called in-message DNS cache, which processes the raw passive DNS data as it comes in from our sensors. And this is after it's passed the query response state inspection, and this program is now going to perform the passive bailiwick algorithm that we described earlier, and as that data comes in from the sensors. And the second source of data comes from the GTLDs that make daily zone file dumps available. So for instance, you can go to VeriSign or Affilius and get access to daily dumps of their entire zones because of the contracts they have with ICANN that requires them to do so. And the third source of data comes from DNS zones, whose administrators allow us to perform zone transfers of their zones. This is currently our smallest source of data, and it's mostly just the IC.org zone. And we're interested in adding more data via this method, since it's very cheap and easy to process in this manner. We then have data loaders that process the passive DNS data into batches of individual database rows and columns, and then connect to our Cassandra cluster in order to insert the processed data. So we have in-message DNS cache, which parses. I'm going to quickly go through the what it does, and then we'll get into the demo as soon as possible. It's a standalone program that reads the raw passive DNS data and parses each DNS message into a stream of individual, what's called resource record sets, and then we apply a series of filters before inserting each RR set into an in-memory cache. And these filters eliminate roughly 50% of the of data that we would otherwise have to store in the database. And RR sets that pass all the filters are then inserted into an in-memory cache, which we've tuned to store about 8 to 12 hours worth of data. And finally, the cache is expired in a strict first in, first out order, and these expired RR sets are sent over a socket, so the output can be stored for later processing and insertion into the DNS database. I think I covered this. So we sign up for the zone file programs, and we then we get the zone file dumps, but these are just the NS delegations. So in the .com zone, we see Google.com has these name servers, but that zone doesn't include all of the records that Google.com wants to serve, obviously, since the DNS is hierarchical and distributed. And then we can use passive DNS to fill in those gaps in the lower child levels of those zones. And this provides us with the TLD data provides us with about 8 gigabytes of DNS data every day, and the passive DNS is probably a whole lot more than that. And we also operate a DNS server that slaves a few zones like IC.org, and then when those zones get updated, we via AXFR or IXFR, zone transfer, and when those zones are updated, they get archived and processed and inserted into the database. This is a crazy, well, that's scaled poorly, but that's a crazy diagram of our architecture, and this will not be on the quiz. We apologize for that slide. Now we can start the demos. How much time do we have left? What time is it? It's 10:23. Thank you. I'm going to switch configurations real fast. Okay, this is the web interface. This is in pre-beta mode. Okay, let's see what we can find. Our domain name search allows us to do wildcard matches, which I don't think any of the publicly available passive DNS, searchable passive DNS databases allow you to do wildcard lookups. So this is a kind of a neat new feature that we've implemented. We're going to look at star.google.com, and we're going to only look at the records that are present in the top level com zone. So this means essentially name server delegation records and address records that are necessary for reaching the google.com name servers. So if we see anything out of the place in this particular domain, in this particular TLD, we know something is up. So here are the 4 matches that we get. Note that we have up to 4 timestamps associated with each match. This one has 4. These have 2 and 2 each. And we have a pair of first seen and last seen timestamps for data that was seen by passive DNS, and a separate set of timestamps for data that was seen in a zone file. So this indicates that this first match right here indicates that the google.com NS delegations were seen with these records from both the zone file and in passive DNS. And these down here say in zone file. So that means that without the other 2 timestamps, this indicates that these records were only seen in the .com zone. And if they weren't seen in passive DNS, that means that we might have a mismatch between the com servers and the google.com name servers. So we see these 3 records, A, B, and F.L.google.com, which are kind of interesting because these exist in the com zone, but not in the google.com zone. So let's click on this. And we get matches for 2 domains, 20comments.com and antifavlc.com. And supposedly Google is the name server for these names, or for these domain names. So let's click on this one, and we get a NS delegation for this domain. And supposedly, according to the .com zone file, this domain is hosted by Google, GTLD servers, and HRoot. For all the people that know about the DNS, this is an incredibly unlikely event to occur legitimately. So it looks like someone has invented a rather creative method of parking a name. And we can do some more clicking around, but I'm going to skip the rest of this example so we can get into some more interesting things. But basically there's a bunch of weird people out there that claim the root servers and the .com servers themselves are hosting their zones, which they don't. They only host the delegations to those zones. Okay. I am not a security researcher, but some of my best friends are. A good friend of mine recommended that this particular audience would be interested in all of the names that are hosted by SoftLayer. Apparently it's some sort of a colo hosting provider or something that for some reason people really dislike. So let's see what happens when we want to look up all the names that say SoftLayer's DNS servers serve. So we're going to do what's called an inverse query or an inverse search. The DNS originally had something called iQuery that worked very poorly, and apparently you have to build giant databases to support this. So we're going to put in a name, ns1.softlayer.com, and we want to know which domains they host. And here are 1,000 records. This has probably tripped over the maximum limit that the web interface has. So they must have a lot more than that. So we see all these different domains hosted by them. I was going to show you another SoftLayer example. I basically need a /16 that belongs to someone of interest. Unfortunately, I neglected to look up that information, so I'm going to use, should I use ISC as an example? Okay. Let's look up an IP or network match. I'm going to put in ISC's /16 and perform a search. Now this is really cool because it did it really fast. It eats /16s for breakfast. So here are a whole bunch of names that go into our ISC's namespace. There's a whole bunch of crap here. Someone is hosting a lot of domains for some reason. I can't imagine why that would occur. But here's basically all of the domains that are pointed into our address space. And this is interesting because the DNS is a forward delegation tree, so you don't really know who's pointing into your address space. So this is a very excellent monitoring application to keep an eye on who's claiming to host something in your address space. I think that's about it for this particular set of demos. So I think I'll switch over to Paul Vixie. And I think we can turn off the projector now. So I don't think Paul's going to use slides.
Thank you, Robert. It's true I'm not going to use slides. I had some, but they were terrible, so I decided that rather than being distracted by them and not using them for anything, I would just talk. So this passive DNS stuff is very cool. I want to thank Florian. Again, he's not here, but he's been here. He's come to DEF CON before. Some of you know him, for coming up with this idea. And I want to admit, once again, when he first told me about it, I thought it was a terrible, terrible idea until I saw the ways that it could be used by e-crime fighters, whether law enforcement or freelance, to go find out who's doing what to whom. DNS is fairly often used for bad stuff. In fact, it is universally used for everything that happens on the internet, and so anything bad is also using DNS. It bothers me that people that are trying to hurt me get to use a protocol that I helped, I had a hand in, maybe some software, and they're using a global system that I'm helping to keep running in order to execute e-crime. So last time something like this bothered me was in the mid-90s when I created something called MAPS, which some of you may recognize as spam spelled backward. It was the Mail Abuse Prevention System. It's really unlikely that any of you has ever before now been in a room with somebody who's been sued more than I have. And that's a result of me publishing reputation data about SMTP servers, and other people subscribing to that reputation data, which we called an RBL, and they would subscribe to that either by BGP or with DNS and tell their send mail or postfix or whatever, gee, if it appears on Vixie's list, then you can just bounce all mail that comes from there. And the problem is that the people that were on my list didn't want their mail to be bounced, and they found that stopping the spam that was coming from their networks was hard, whereas suing me was easy. Anyway, my wife has assured me that this won't happen again. So as a result of sort of all that, 10, 12 years later, we sold MAPS. They're still selling the old RBL. There are probably 100 other RBL-like things. I guess the new name for them is the DNSBL, but it'll always be an RBL to me because that's what we called it. And we're all getting as much spam as we ever got. So I've noted that email is less reliable than it used to be. A lot of false positives. A lot of people have abandoned RBLs in place and put a wildcard in there so that their subscribers bounce everything until they stop subscribing. I will tell you that the really, really oldest RBL, the very first one, is called rbl.maps.vix.com. We only used that name for about 6 months. And then we got mailabuse.org or whatever and started using that. That's in Vix.com, and people still send queries to it 12 years later, 12 years after it was turned off. It's rather frustrating. I suppose I could wildcard it and then they would all bounce all their mail, but that seems rude. So instead I collect the data and I give it to the passive DNS effort. Anyway, noting, again, that e-criminals need DNS as much as the rest of us do. And not only do they need DNS, they need it to work as well for bad guys as for good guys. I have decided to try again, except this time We're not going to create a reputation feed that is subscribed to by email servers. No, no, no. We're going to create a reputation feed that is subscribed to by recursive DNS servers. The things we're going to black hole this time will not be the IP addresses of other people's mail servers. They will be the domain names that the bad guys need for e-crime. So if you go to our website, www.isc.org, you'll see that while Robert was talking, I hit the publish button on a blog entry that describes all this. We're also headed for a Q&A room after this if you'd like to talk more about it then. But just to hit the high points on it, we will not be sued. ISC is a nonprofit 501c3. We do not like being sued, so we're not going to publish any content. I know where a lot of bad domains are, thanks to Robert, but I am not going to make a list of them and publish them because that's the way you get sued. Instead, we are going to publish patches. In fact, we have just published patches for Bind 9, so that if you're running a Bind 9 recursive name server, you can apply what is about a 600-line unidiff and get a new feature, which is to subscribe to a response policy zone. Yes, we are going to use DNS zones as a way to propagate sort of policy and reputation information about other DNS names. It's a lot like the RBL in that sense. It doesn't slow the name server down. It has not caused any crashes or core dumps in the last couple of weeks anyway. It will be... No cert advisories yet, it's not my code. Let me think what else. The spec is open, no patents, no license, no nothing. Anybody else, any other recursive name server operator, and nominum, I'm talking about you, who wants to implement this can do so without having to pay any tithe. We have talked to a bunch of content providers. There's something out there called an RHSBL. It was, I guess, first popularized by Jeff Chan of Serble, but it is like an RBL, except it refers to the stuff after an @ sign rather than before the @ sign or whatever. I'm not sure what the right hand refers to. But anyway, it's lists of bad domain names. Spamhaus has one, Serble has one, a bunch of other companies have them. They didn't have a distribution channel for it, now they do. They're going to be able to use this, because we're creating a single universal format that any recursive DNS server could implement and any reputation provider can publish with, in order to have it be that if somebody is doing something bad from a certain domain name, and if any of your users are using, let's say, Windows, and if they click on it, they will become infected, and you can't stop them because we are all just barely evolved monkeys and we will click on anything that moves, you can make sure that the DNS won't work, so that when they click on it, nothing will happen for them. I hate that we have to do it this way, but since we have to do it this way, I've decided to make it possible, make it easier, and to launch yet another multi-billion-dollar industry which I will not monetize in any way. My wife has asked me questions about that too. So, we have some time for questions, either about Robert's stuff, which I think is really interesting, or my stuff, which I think is sort of interesting. How many minutes? We got 12 more minutes. So, this room is much more full than I expected because the EFF party went until 4 a.m., so you must not have been there. And they're talking about this cool badge in some other room, and I thought all of you would be in there listening to that. Maybe there was no room. Anyway, I'm hoping that there are questions. We have time. Question?
He asked about covert channels via the DNS. We do notice what appears to be covert channels that are conducted over the DNS, and these happen to be really annoying for us. So when we find them, we tend to blacklist them so that they don't enter the database, because they obviously have the potential to evade the cache, because all of the names and data are unique. So we don't want to take anyone's YouTube downloads via DNS and shove them into a database. We haven't really tried to discover covert channels using the passive DNS data, using the raw data itself. As I mentioned, I'm not a security researcher. I just build tools that security researchers can use. So I'm afraid I don't have any really hot examples for you. Any other questions?
Wait a minute.
Oh, okay.
I want to follow up on that answer. So we've described a database that was built on a bunch of passive DNS stuff. It turns out that the raw data was our original product. The Security Information Exchange is an Ethernet switch full of UDP broadcast traffic. So all the data that we get from our sensors, we play as UDP broadcasts on a sort of an Ethernet switch that's in our data center. And then we listen for that on another port on the same switch. And we invite other people to come plug their computers in and listen to that. So it's basically a tap point on our raw data stream. We not only take the raw data, but after we've run it through various filters like deduplication or this QR stuff or various filters, are also touching down on VLANs on this private switch. Somebody who is in our data center and plugs a computer into our switch is able to see not just the raw data, but as we process it and rebroadcast it, they can see it as it gets more and more refined.
Intermediate products.
The intermediate products, thank you. So we hoped that that's all we would have to do and that somebody else would come build this database. In fact, I hoped Florian would come build a database because we have a lot more data than he had, and he was good at building databases, but he's kind of on to other projects by now. So we have built a database, but if you really wanted to look for covert channels, the raw data is right there. If you're a commercial entity, we will charge you a port fee. On the other hand, if you're a university researcher or a hobbyist or whatever, and we can vet you, we will probably waive the port fee because we want this data to get used. So as far as covert channel detection, the fact that we're not doing it should not cause you to think it cannot be done. We have more passive DNS data than anybody, and we're going to keep doubling it every year until Moore's Law explodes. More questions about anything?
We have a bulk query.
Question?
Oh, sure. He asked if there was automated queries, and we do have an interface for doing bulk automated queries. It's via a simple HTTP RESTful type interface. You construct a URL and download it, and it will give you back either JSON or some binary format, or we can even convert it to an ad hoc text format. But yes, we actually implemented that bulk interface before we did the web interface. And if you and at some point we'll be able to allow external entities to query that interface. Any more questions? That's a good question. Yes, when it will be available. We will probably start up a beta period right now, and we're interested in reaching out towards people that are interested in hacking on a beta type interface. Fellow in the back.
You mentioned that for your RSS you filter 50%. Is that, what is in that 50% that you're filtering?
He asked, what is in the 50% of the data? Sorry? Okay. Yes, what is in the 50% of the data that we throw away? The big thing that I noticed when I was building this is spamhouse.org generates a lot of data because it doesn't follow the usual distribution of data that it normally gets. A typical DNS. Okay. You'll typically see about an 80 to 90% cache hit ratio for your typical DNS server, but certain zones in particular generate a huge number of unique queries. And Spamhouse is a very good example because it's a DNSBL and it's the key that's being queried is an IP address, and botnets are constantly generating all of these different queries. And then once I had done that, I had implemented a blacklist that allows us to exclude certain domains and subdomains from further processing. And then I looked Then I started sorting by the domains that were generating the most data. And I found things, I believe Yahoo has a load balancer that chucks a ton of address records into a query, and there's this combinatoric explosion of different possibilities. And that was such a large volume that I blacklisted that particular zone that they used as well.
Tell them about Facebook.
Oh, Facebook, that's a good one. Facebook has a chat feature. Now they have this web chat thing. You can instant message your friends. And the neat thing about Ajax is that the web browser developers have decided to implement a limit on the number of persistent connections you can make. And to get around this, web developers have discovered that you can use a wildcard CNAME record and use different names for your server. So someone at Facebook decided to use this in order to make multiple connections, because you could have tons of Facebook profiles open in your same browser session. You need to chat with all of your multiple identities. And the fellow who wrote the code that generates the new name to use decided to use a 10-digit random number. So we ended up with, I think, around 5 megabits continuously of these Facebook records that were being looked up. They were totally useless, and they had a 1-hour TTL. So I can't imagine what's happening to the recursives that are kicking out all of those records. So we blacklisted that. That's a huge proportion. Let's see, the other types of filtering that we do is we are not really interested in generically named pointers records. So your ADSL host 192 whatever bellsouth.net, well, there's tons of that. So we use something called the enemies list to filter that. And there's a very nice fellow by the name of Stephen Champion who maintains approximately 50,000 regular expressions that we use to filter that data. And that accounts for about 50% once we do the very aggressive caching. What was your follow-up question?
You said you aged using a FICO, and I noticed there were no TTLs listed in your database. Do you just find TTL to be completely irrelevant as a DNS?
TTL is not a very strong part of the uniqueness of an RSet, so we don't actually store that. In certain of our intermediate products, we do maintain the TTL, but we don't actually insert that into the database because it can cause a lot of copies of the RSet to occur. This fellow.
Does your forward lookup support Plot 8 records, and does your prefix lookup actually support V6?
The forward look. He asked if we had the ability to look up Quad A records in the forward interface and the ability to look up IPv6 prefixes in the reverse. We support, it's fully generic. We support all possible DNSRR types. It's just an integer, and the web interface has some cute little drop downs to select the most commonly used type. And the reverse search is done based on a byte prefix, so we can support IPv6 prefixes, IPv4 prefixes. We can start doing name prefixes and other generic data. I believe we're almost out of time. Do we have any? Okay, more questions? Yes. Yes. Sure. You can't search for regular expressions, but you can certainly search for exact matches or prefixes. Okay.
Questions about the sensor network? It's true that we can't name all of the parties who are giving us data, but on the other hand, some of you should be giving us data. This is all open source stuff, and you can see it's for a good cause, so take a look at our website, sie.isc.org, and find out if you should be running a sensor. Some very large ISPs are running sensors. Some universities are running sensors. I love it when we get a sensor that covers an underground dorm complex, because those people really will click on anything. But we always need more. I'm not going to miss this opportunity to do some outreach. If you have data, please share it. Not just recursive servers. If you have authority servers, we can take your queries. I don't care about your answers because those are predictable based on your zone content. But I'd love your query stream on authority servers. I'd love your query and response stream on your recursive servers. We're going to open up SIE to other data formats soon. We're going to be looking for NetFlow, DarkNet, Whois, since we've got somebody from Aaron here. It's all kinds of stuff that should be shared in order that we can cross-correlate. Andrew Freed last year gave a talk about how he was able to use SIE data, the passive DNS, and our spam trap feed to do cross-correlation and find botnets. So if you have spam traps, or you might be willing to start up a spam trap, talk to us and we'll help you sort of extract all the interesting body URLs and format them in the format we need, and then we'll share them with the security community. So the answer is the sensor network is not public because people don't like to be thought of as targets. They don't want to paint targets on their back. But we won't tell anyone who you are if you're sending us data, so please send us data.
To add some concrete numbers. Oh, we're done. All right.